Thank you for your introduction. Today I'm going to talk about synthesizing polynomial loops using a geometric approach. Also, I would like to mention that this work is joint work with my supervisor Fatemeh Mohammadi and Rémi Prébet. Okay, before going to technical things, I would like to explain why program synthesis is useful. First, what is program synthesis? Program synthesis is the process where you can automatically generate a code that meets given a high-level specification. In other words, instead of writing a code by yourself, you can describe what the code should do or what constraints the code should satisfy, and program synthesis takes care of the rest. Let me give you an example. For example, biologists often want to build models of complex processes, like often have certain mutations lead to disease. Okay, so program synthesis can help them by automatically generating a model that meets the specifications given by biologists. This is very useful for them because unlike computer scientists, they cannot run experiment as many as they want. For them, experiments takes a lot of effort and money. Sometimes even they don't have enough material to do many experiments. Okay. In this work, I will only focus on synthesizing polynomial loops that satisfy given invariants. Let's say example. In this example, there are two invariants are given, and the map is not fixed. So we need to find the correct values for these parameters, such that these invariants hold after every iteration of this loop. For example, if you choose these values instead of parameters p1 to p5, this loop satisfies these invariants. Okay, so in the rest of my talk, I will explain how to find these values, these coefficients. Okay, so what is a polynomial invariant? Polynomial invariant is a polynomial equation or a polynomial inequality that holds before and after every iteration of a loop. Okay, in my talk, I will only focus on polynomial invariant equations. For example, that map of this loop is given by polynomial map. X gets z squared, y gets z cubed, z gets x plus y. For this loop, we have a polynomial invariant of degree 3, y squared minus x cubed is equal to 0, which means that if you plug the initial values inside this equation, it holds. After one iteration, the values of x, y, z are 1, 1, and 2. They also satisfy this equation. After two iterations, the values of x, y, z are 4, 8, and 2. They also satisfy this equation, and so on. Now I would like to mention some related works about synthesizing polynomial loops. Okay, there are four types of works. In the first three types, they restrict their loops to be linear, which means that that map of a loop is linear. In the first type, they only consider binomial invariants. Binomial means is a polynomial that is a difference of two terms, and each term is a product of variables. In the second type, they consider only one quadratic invariant. A quadratic polynomial is a polynomial of degree 2, and in the third type, they love any polynomial invariants. Okay. So the last type is our work. So in this work, we can synthesize any polynomial loops that satisfy any any set of given polynomial invariants. So there is no restriction for assignments and invariants. And the first two type, they prove that if there exists a non-trivial loop, they can synthesize it. However, in the last two type of work, we might not be able to synthesize a non-trivial loop. Okay, so now I'm gonna say our contribution. So we would like to synthesize a loop. So then we convert this problem into finding a solution of a polynomial system. For example, so let's take our ongoing example. So we would like to find the correct values for these parameters. So if we use our method, we can give you finally many polynomial equations. For example, in this case, these four equations, such that each solution of this system gives you one correct values for this parameters p1 to p5 in this case. Okay. So we would like to synthesize a loop such that this loop satisfies this polynomial invariant G, and we change this loop a little bit. So in the second loop, we have one more set of variables, y, and that map is fixed. And our claim is that G is the invariant of the first loop when G is the invariant of the second loop. Okay, so which means that we reduce the problem of finding coefficients of that map into the problem of finding initial values. Okay, so that then our problem is like how to compute the set of all the initial values such that given equations are invariants. Actually, this is our previous problem. Now I'm going to explain it briefly. So by the definition of invariant polynomials, G is an invariant of this loop if and only if g of a is equal to 0, g of f of a is equal to 0, g of f of a is equal to 0, and so on. From this statement, we have this definition. For given polynomial map f and g, we define the invariant set of f and g to be a set of all points such that g of x is equal to 0, g of f of x is equal to 0, and so on. Also, you can easily see that g is the invariant of this loop when the initial value of the loop is contained in the invariant set. Therefore, if you would like to compute the set of all the initial values such that given equations are invariants, then it's sufficient to compute invariant sets. Okay, now let's see how to compute invariant sets. By the definition, this invariant set is exactly the same as the common solution of these infinitely many polynomial equations. In algebraic geometry, there is a property called the theorem property, which says the following. Every system of infinitely many polynomial equations has a finite subsystem with the same solution set. In other words, even if you start with the infinitely many polynomial equations, only finitely many of them are needed to describe the solution set. If you use it, then there exists some natural number n such that this invariant set is same as the common solution of these finitely many polynomial equations. Okay, now let's see example how to compute invariant sets and why it's useful. Okay, so for this case, we would like to compute the set of all the initial values such that G is the invariant of this loop. So first we compute G of f and we check that the solution of polynomial equation G is not same as the common solution of polynomials G and G of f. For example, you can check it by using tools from computational algebraic geometry, such as corner basis. Okay, that's why we need to check the next case. The next case, we compute G of f of x. This time, these two sets are exactly the same. Therefore, our invariant set is defined by polynomials G and G of f. Moreover, G is the invariant of this loop if and only if the initial value a1, a2 is a common solution of polynomials G and G of f. Okay, so now let's go back to our problem. So we would like to synthesize a loop. Also, we have equivalent problem. And now we know how to solve this equivalent problem. It's exactly the invariant set computation. So then we have the following theorem. So if G is the invariant of the first loop, when the initial value A and the parameter of that map is inside the invariant set of the polynomial map of the second loop and polynomial G. Okay, and you can easily also see that this invariant set is defined by these finitely many polynomial equations. If you plug the initial value and the parameter inside these equations, then you obtain this one, which means that okay, every solution of the finitely many polynomial equations shown here gives you one correct value for these parameters b, such that if you plug that values inside these parameters, the synthesized loop satisfies this given invariant. Okay, let's say example. Okay, so there are two invariants are given, and we would like to find the correct values for these parameters p1 to p5. And we reduce this problem into finding initial values such that given equations are invariants. Now our parameters are inside the initial values. This is exactly an invariance at computation, as I said before. So in this case, this invariance set is defined by 6 polynomial equations. And if you plug the initial values inside here, so we have 6 polynomial equations with variables p, okay? And the first two equations are identically equal to 0. The third one is a quadratic polynomial. The fourth one is a cubic polynomial. I didn't put the last two polynomials here because the last two polynomials are quite large. Okay, so far we haven't synthesized any loop. We just give some system of linear equations that defining the parameters p. Yeah. So now the next step is like we need to find the rational solution of a polynomial system. So finding an integer solution of a polynomial system is undecidable in general. This is actually a very famous problem, which is Gilbert's 10th problem. For rational case, it's an open problem in general. So, however, in practice, for many polynomial systems, we can actually find the rational solution. Now, let's see what kind of methods we can use to find the rational solution. The first one is a symbolic method. So it's okay. Let's explode the structure of a polynomial system. The idea is that so we have this complicated big polynomial system. So we would like to decompose it into simpler subsystems. For example, if you see this, if you use our ongoing example, so we have these 4 polynomial equations. The last two of them are quite large. So we can decompose this system into these 5 subsystems. 3 of them are actually linear systems, and the last 2 of them are almost linear. Okay, so then it's much easier to solve these systems, these subsystems. Okay, the next one, numerical methods. Okay, the idea is similar. So we have this complicated polynomial system. So in this setting, it's called a target system. And we have a starting system, which is much simpler to find a solution. And if you use this homotopy continuation, you can track the solutions of a target system from a starting system. Okay. For example, there is a package called homotopy continuation in Julia. You can use it to find a solution. The last one is SMT solvers. SMT solvers can determine the satisfiability of logical formulas combining with Boolean logic with mathematical theories such as integer or real arithmetic. For our case, we have conjunction of polynomial equations, and we would like to check whether it's satisfiable. For example, Z3 can check it. If Z3 can prove if it's satisfiable, then it can give us a rational solution, and we can use it to synthesize a loop. In our case, the last method actually works very well on our benchmark set. Okay, now let me explain some experiment results. We implemented our code in Macaulay 2. Okay, let me explain the table. The parameter S represents the number of non-zero equations defining our parameters p, and this also represent the number of solutions of our polynomial system, which is exactly the same as number of possible loops. Okay, the parameter n represents the number of variables in a loop. Parameter m represents the number of invariants given invariants, and the parameter d represents the maximal degree of polynomial invariance. If you see the table, for most of the cases, our algorithm terminates. Okay. In the second table, we present timings in seconds. So there are 2 timings. the first time is the running time of our algorithm. The second time is time of Z3. So by using our algorithm, we can construct a polynomial system that gives you correct values for these parameters inside that map. Okay. And now we have this polynomial system that we can use Z3 to find the rational solution and actually synthesize a loop that satisfies given invariants. If you see the table, for most of the cases, if our algorithm terminates, Z3 can actually find the rational solution. And also this benchmark examples, we got it from these three papers. So these three papers are exactly the same as the papers in the state of art slide. Okay, now let me summarize. So first we we explain a method how to convert the problem of synthesizing loops that satisfy given invariants into the problem of finding a solution of polynomial system. And after that, we actually gave some methods to find the rational solution, which is useful because we need to find the rational solution for our polynomial system, which is constructed by our algorithm. Also, we have some ongoing works. The first one, the polynomial systems defining invariant sets have some specific structure, and we would like to use that structure to compute invariant sets in a faster way. The next one is we would like to synthesize non-trivial loops. As I said before, we might not able to synthesize a non-trivial loops. The last one, in our work, we only consider equation invariants. So of course, the next step is like consider invariant inequalities. Therefore, our problem is that synthesizing polynomial loops that satisfy given set of invariant inequalities. Okay, thank you for your attention.
Okay, so are there any questions? Okay, so maybe to kick things off, I can ask the first question. So first of all, thank you for your talk. And then I noticed that basically your algorithm, it either works within seconds or you more or less immediately run into a timeout. Do you have any idea what the characteristics of the problems are where your algorithm works well versus those where you run into this 300-second timeout?
It depends on as monomials, we need to synthesize our loops. Like if the number of monomials is okay, let's say fewer than 6, then it usually terminates in seconds. If a number of monomials is greater than 6 or 7, it usually reach the time limit.
Okay, thank you. Any other questions? That does not seem to be the case. So thank you again for your presentation, and thank you for being here with us this morning. And yes, let's give him another round of applause.
Thank you.